share my screen now?
And yes, you could share your screen. I'm gonna introduce you here. So we have a good number in the classroom. And so today, as I just mentioned, I've been waiting and looking forward to this lecture. I know one of my colleagues is also looking forward to this, Ryan Hayes, general chemistry analytical jock. Loves fluorescence and other analytical techniques. So our speaker today received his PhD degree in 1998 from the University of Bonn, Germany. From 1999 to 2002, he was a postdoc at the University of Toronto in Canada. Then he began his independent career at the University of Mainz. Is that Mainz?
Yeah. Mainz.
Yeah. Mainz. And RWTH Aachen University, hopefully is correct, in Germany. Then he moved to the University of Calgary in Canada in 2006. And then since 2017, he is a full professor and Canada Research Chair at York University in Toronto. Research interests are focused on molecular organophosphorus, pi conjugated materials, as well as supramolecules and polymers for sustainable energy applications and sensing. Today, his focus would be on Lewis acids and how we can determine Lewis acidity using fluorescence. So it's a pleasure and a privilege to have you join us here today.
All right, thank you very much for the invitation and the nice introduction. I have a few more slides, basically doubling up a little bit, but I'm filling in a few more details just to give you an idea of where I came from. So let's start here. So how did I get here? So I mean, maybe my career path is maybe something that can maybe be described as a series of maybe fortunate events. Because really after high school, I didn't really know what I wanted to do. And back in the day, I was also mandatory military service in Germany. So I did that. And then I still didn't know what I wanted to do. And I was basically forced to decide on a dime what I wanted to do. And basically entering university was probably the only option on that short notice. And I thought, oh, maybe to do medicine or maybe do biology. And then I realized, oh, there's an entry limit. So you can't actually just decide that because they're decided for you if you can access these very popular degrees. And in Germany, you can actually start studying medicine from the first year as well. So in Germany, it's really you start your degree at the first year and you go on straight. Undergraduate degree didn't exist at the time when I was there. So the end goal was always at least a master's degree or ultimately I ended up in chemistry because that was open to me. And basically it was more or less assumed that this will go all the way to the PhD because Germany has a lot of chemical industry as well. So what did I do there in terms of research? It was really fundamental phosphorus chemistry. So basically making some bizarre molecule that people said you can't make. So absolutely no practical value. It's just pure science value. And here's a few examples here. So maybe I'll just highlight this one here. So this is a compound that people predicted you cannot make a carbon-based molecule that has a lithium and a fluoride substituent because lithium fluoride will form immediately and it will fall apart. But if you incorporate this into a phosphorus-containing background, you can actually stabilize it and you can even crystallize it, as you can see here. This is the crystal structure of one of those compounds. So very esoteric chemistry, but from a structural and bonding standpoint, quite interesting. Then after my PhD, I decided, okay, what do I want to do next with my life? I said, I don't know, but doesn't matter. You can always do a postdoc because back in the day, industry and academia, they always appreciated a postdoc experience. So I had no time lost there. And I decided I wanted to do something that is maybe slightly different what most Germans did at the time, which is basically going to the US and do a postdoc there. So I ended up in Canada, where I then switched my research focus and had more of a materials research to it, and so I had more or less two major projects that I was working on. So it's basically trying to put metal components into polymers and materials. So here's an example where we try to use the reaction that's well known, that you can take an alkyne and react it with cobalt octacarbonyl. So you make these clusters here, and then ultimately make larger polymers that have a large content of metals, and ultimately the idea was to combine the beneficial properties of polymers, that you can shape them in a different form, but also have metals in there, so you can maybe pre-shape it in a certain form and then make nanostructured metal ceramics out of the material. The other project I was working on is shown here. This was based on ferrocene containing molecules that have, in this case, a tin bridge. This is a strained molecule, and can ring open that and make polymers again that have a high degree of metal in the backbone. So that's sort of a lot, again, from an educational standpoint. I had really fundamental main group chemistry or phosphorus chemistry, and then got a flavor of the materials world. So from my independent career, and I said maybe I can combine that in some way. And as mentioned in the introduction, I first started off at the university in Mainz. This position was called a habilitant. I decided to go back to Germany at this stage because it's a slightly different setup than a North American setup. You are embedded in a big research group, and you're allowed to do your own research there. So I didn't have to worry about applying for research funding or even spend a lot of time on teaching. So I could really focus on the research, and which was very important because I pivoted again. Originally, I wanted to build on the work that I did as a postdoc, but these things didn't quite work out, and I ended up in the field that I'm working on right now, and I'm going to tell you about in a few minutes. So since I was embedded in a big group, I was tethered to my mentor, who actually ultimately after a year decided that or got a position at the RWTH University in Aachen in Germany as well. So I had to move with him. This is why basically I spent a year in Mainz, and then I moved to Aachen again in the within the same group. But the ultimate goal was always to go back to Canada at this time, and eventually there were some positions advertised that were interesting, and ultimately I interviewed at the University of Calgary, and they offered me a job. So I started there my Canadian career, first as an assistant professor, and then I rose through the ranks up to a full professor. And then, as mentioned, in 2017, I moved to York University, where they also offered me this Canada Research Chair position, so I could focus more on research with my research program, and I could also choose a title for my chair. So it's basically, I chose it to be sustainable organic main group materials, to really capture sort of the things that we're doing and also my background. For those of you who don't know where York University is, it is really still within the city limits of Toronto. It's at the very north border. So basically, the north edge of campus is also the north edge of the city. But certainly, we now have a subway that leads us downtown, so we can benefit from living in Toronto, which is a very multicultural place to live in. All right, yeah. So basically, I was just meandering through my career. I never really had an active choice in this, that I wanted to do this. It was really more driven by things that I didn't want to do. So, and ultimately, that's maybe a career path for you as well. And I think I'm quite happy where it led me. So I probably would do a lot of these things again if I had to do them. But let me just switch over to the science side of things. Again, being able to focus on the research was very important at the start of my career, because as you've seen, my background is more on the inorganic material side of things, but in my independent career, I also became an organic chemist. So I needed to learn a lot of this chemistry, and it was good that I could actually do it firsthand in the lab myself and spending a lot of time in there. And ultimately, we're now working in an area that involves conjugated materials, and these are very popular materials because you can really use chemical synthesis almost in a Lego-based approach to assemble things and install functional properties through chemical synthesis. And you can do that by very simply modifying substituents, or you can come up with some very unique structures that quite a few people in the world are now working on, making big systems. You take a planar pie system, you put it on the side and bend it around and make a hoop, or you just bend it somewhat and you make a bowl, or twist the system. That all has a very strong impact on the electronic properties of these backbones. That ultimately also addresses the aromaticity or anti-aromaticity of these backbones, and people are also playing with systems that have unpaired electrons in there. That has also a very strong impact on functional properties. But I'd never let go of my roots. So obviously I'm still combining that, and we're trying to actually put phosphorus into these conjugated materials. And main group elements in general can add also quite a bit of value to these materials, because you can have elements that are quite electron rich. So you don't need to worry about installing additional substituents, because the element itself has maybe a lone pair that can electronically impact the electronics of the pi conjugated carbon-based system. Or you can put something in like a boron, which basically removes electrons out of the scaffold. And you can also do that with higher role main group elements like phosphorus and silicon. You can also build them into a system, and I'll show you that on the next slide, to create an acceptor environment, despite the fact that they're actually inherently fairly electron rich. It really comes down to how you incorporate these main group elements into a backbone, and what the geometry ultimately is in these systems. If you want to learn more about this, I have to put a little bit of an advertisement in here. So there's a book that my good friend Frieder Jäckler and I were postdocs in the same group, and he works on boron conjugated materials. He is at Rutgers University. So we edited this book, and basically you can see what main groups elements across the periodic table can add to functional materials. Now, again, phosphorus still plays a major role in this 5-membered ring system. Phosphol is a main component in many of the materials that we're working with. And phosphol is very interesting because it has completely different properties from pyrrole, which is its little brother. Just obviously, you go in group 15, one element up, you have nitrogen there. In contrast to pyrrole, phosphol is actually not planar. It's pyramidal at the phosphorus, and ultimately has a much weaker aromaticity as well, because the lone pair doesn't actually delocalize with the pi system. This is only a side note, but in our context, there's a much more important interaction, and it also plays a major role for my main topic today, is this interaction that because of the pyramidal geometry of the phosphol and the electronics that the orbitals of phosphorus brings to the table, you actually have a possibility that an antibonding orbital, that the phosphorus carbon antibonding orbital here, can interact with the pi system. So energetically, that's possible because it's phosphorus, and because we have the geometry set up in a way as well that we actually now have a nice interaction between these two components here, which ultimately gives you a bonding combination and an antibonding combination, and this is called a sigma star pi star interaction. And ultimately what happens is this pi star orbital is lowered in energy. And this orbital is also a very important one for our materials, because it's mostly the LUMO in most of our materials. So basically this interaction has a very strong impact on one of the frontier orbitals that is key for a lot of the properties that we see, and also the functional things that I'm going to highlight you today in the context of Lewis acids. So over the years, we've developed quite a few materials. This year is one of our workhorse building blocks, and it also will feature today in the talk, is the dithienophosphol. It's an extremely fluorescent compound. So we spent almost over 20 years on it, on this, and it still surprises us to this day with new things we can do with it. So it's a really never ending. It's a golden egg, basically, or the golden goose that keeps on laying eggs that we can use. We're also interested in bridging the molecular world into the materials world, so we look into some self-assembled materials. In another branch, we use nitrogen-containing scaffolds as well, because they have very strong acceptor properties, and not so much luminescent, but they have really good developed redox properties, and we use that in batteries. So we use these kind of materials as battery electrodes. We're not alone in this field. Obviously, there's other people that working in these, and here's just a selection of some interesting molecules. There's much more out there, but just to show you that you can incorporate phosphorus in a variety of these organic materials, and very often, more often than not, that they have really value-added enhanced properties over the purely carbon-based materials. And one other important feature is when you incorporate phosphorus. So it's basically, you have the possibility to do chemistry with it, particularly when you start up with a trivalent phosphorus, which has the lone pair. So if E is a lone pair, you can do very simple chemistry. You can oxidize it, put an oxygen in here or sulfur, or you can put Lewis acids on there, and ultimately create a second bond. And that second bond also has an antibonding orbital that can then also interact with the pi star system. So we can actually install a secondary sigma star pi star interaction and modulate the energy level of the LUMO and make it a much stronger acceptor species in this case. And this is shown down here on the bottom as well. So basically a very simple molecule. And we've only done some phosphorus chemistry here. We've done also a little bit of sulfur chemistry, which basically does the same thing. It installs 2 exocyclic substituents that also bring their sigma star orbitals to the mix. And ultimately, we can have a scaffold that starts off with 1 sigma star pi star interaction. If you only have a phosphorus, the phenyl group here and a lone pair there, and the sulfur is not oxidized. Or we can oxidize it and put something on there. And the end result is that we can make a wide series of materials that have different photophysical properties. And that's basically the end result of just modulating the LUMO or bringing down the LUMO more and more. And so we get in that from a blue emissive compound to a green emissive compound. Just a space filler here. I'm not going to talk too much about it, but this is sort of what we do in terms of nanomaterials. So we have some self-assembled fibers here. This is an organogel material and then a liquid crystal material here. So that combines the electronics of our phosphor-based materials with some ancillary groups that ultimately gives us some nanostructured materials, which could be very important when you apply these things in practical devices. But today, I was invited to talk about the Lewis acid sensing that we've developed. But this ties in to the things that I just talked to you about, because this is kind of again, it uses the dithienophosphate system and also features the sigma star pi star interaction. All right, so and this is I also have to say that this is a collaborative endeavor with one of my colleagues here at York University, Chris Caputo. He's an expert in Lewis acid chemistry, so he does this PhD with Doug Stephan, who developed the frustrated Lewis pair concept. And we brought our combination, so his expertise in Lewis acids and ours in the development of these luminescent phosphorus-containing molecules. We said, how can we combine this thing? And so we said, well, maybe we can actually see if we can use our dithienophosphols and maybe determine the strength of a Lewis acid in using it in the fluorescence. You know, Lewis acids, by the very basic definition from 1912, but Gilbert Lewis, are supposed to be electron pair acceptors because they're inherently electron poor. They can interact with a Lewis base, basically with an electron pair, and can form a bond. And there's many Lewis acids out there that could be boron based. That's sort of the archetypical main group Lewis acid, but you can also make phosphorus Lewis acidic by creating this hypervalent species here. Note this is a dicationic species, so this also has an electron deficit, but it can also be as simple as an aluminum trichloride or a scandium triflate. As long as you don't have a filled valence shell or a high charge around the molecule, the central element, they will behave as a Lewis acid and accept electron pairs from somewhere. And people have recognized that this is actually also a very nice functional property in chemical transformations or in catalysis. So a lot of organic transformations now are Lewis acid catalyzed. And the main question, obviously, that revolves around this functional application is, how much Lewis acidity do you need, or is there a certain threshold that you need to actually make a reaction go or not go in the presence of a Lewis acid catalyst? So even in the early days, when people started to realize that we can use these molecules as a catalyst or as a mediator for an organic transformation, maybe want to learn a little bit more how strong of a Lewis acid are these things actually. And this goes back almost 50 years here. So there's methods that have been developed. The most well-known, I would think at this point, is the Goodman-Beck method. It's an NMR-based method. What happens here, they use a phosphorus oxy component, so this phosphine oxide. And when you coordinate a Lewis acid, it will coordinate to one of the lone pairs of the oxygen here. It ultimately changes the polarity of the PO bond because you pull electrons away from the oxygen, and ultimately it's a push-pull kind of a system. The Lewis acid and the phosphorus center will fight for the electron density around the oxygen, and if the Lewis acid is strong, it will pull electron density out, and ultimately you will be able to notice that in a low field shift in your phosphorus NMR. That's how the Goodman-Beck method works. The Childs methods was also developed about a few years later than the Goodman-Beck method. A very similar concept. They use this croton aldehyde, and basically, the stronger the Lewis acid, the more de-shielded this proton becomes. So it's basically you determine the delta 1H and determine if it's a large shift, it's a strong Lewis acid. If it's a small shift, it's a weaker Lewis acid. So that's an NMR-based method, a practical method that still people using to this date. There's other methods out there then. Obviously, computational methods have been improved over the years. And one of the ones that people lose quite a bit is actually called fluorine ion affinity, which is basically the reaction of a Lewis acid with fluoride to make a bond. And the idea here is that the stronger the Lewis acid, the stronger the Lewis acid fluoride bond will be. And ultimately, you can quantify the bond enthalpy and correlate that with the Lewis acid strength. This is very limiting, obviously. It will only give you information how strong the Lewis acid fluoride bond is. But if your Lewis acid is not exposed to a fluoride, there may be a questionable value on the result that you get out there. If you use it, for example, for a Friedel-Crafts alkylation or something like this, there's no fluoride in there. So the fluoride ion affinity may not actually be something that's useful for that context. So Doug Stephan, who, as I mentioned, has developed this frustrated Lewis pair concept, then also developed this global electrophilicity index to make it a little bit more non-specific, so broaden it up. So it's basically the energy that is being released when a Lewis acid binds to a Lewis base. So this is, again, a computational method, and ultimately, the larger the bonding energy, that's when the bond is formed, the stronger the Lewis acid should be. That's at least the working hypothesis. Now, what these methods have in mind, or sorry, as a common denominator, is basically they give you one number, an idealized number for each Lewis acid, which in other words, they give you a absolute Lewis acidity. So basically, the Lewis acidity of the Lewis acid X is number. So basically, you get a parameter that defines the Lewis acidity. And then ultimately, if the number is bigger, then ultimately the Lewis acid should be stronger, and then you can rank Lewis acids according to the number that you get by these point measurements. Ultimately, what's the problem here is that permutations or variations of Lewis acids, if they change the structure in solution, for example, they're not being considered, because you basically say the Lewis acid of aluminum trichloride is X, or the Lewis acid strength of aluminum trichloride is X. And ultimately, I already mentioned that the parameter that you get with any of those methods, it may not necessarily be relevant to what you use the Lewis acid for, because it's actually an interaction with two species that don't interact in the environment that you need it to interact. And even more so, if you look at the fluoride ion affinity, it really depends on the computational method that you use and even the species. This is a compound we call BCF. So this is pentafluorophenyl or tris pentafluorophenyl a borane. You get one number, that's great. But even for aluminum trichloride, depending on the computational method that you use, you get a little bit of a variation there. We could say it's around 500. This is perfectly fine. But if you look at the trityl cation, you get a wide range of numbers here already, just by the computational method that you employ. So again, that's 10% difference. And if you have Lewis acids, you want to compare them, your window is way too big to actually compare to Lewis acids. And this opens up the door now for effective Lewis acidity. And this is something we have tackled with our method. We really want to not use to define a specific Lewis acidity for value, like a pKa for hydrogen or hydrochloric acid, for example. We've already shown the effective Lewis acidity is basically what is the result of when you put the Lewis acid into an environment? How Lewis acidic is that environment, and not necessarily the specific species. So basically, the parameter that we get will demonstrate the Lewis acidity. We can still measure this, and we can still correlate that. If it's a larger number, then this should be a stronger Lewis acidic environment or effective Lewis acidity. But what we do is we also consider the environment that could impact this readout. And ultimately, as I will show you later in my talk, the acid rank may actually change as the environment changes. So because solvents can also be Lewis bases, and they can interact with the Lewis acid in solution and quench the Lewis acidity. And this is not being considered in the absolute Lewis acidity. And ultimately, also the permutations, we will throw this in. So we measure everything in solution and summarize that into one number, which is ultimately the effective Lewis acidity, not the absolute Lewis acidity. And why that's important, I want to show you in the example of aluminum trichloride. Because if you use the absolute Lewis acidity of aluminum trichloride, people refer to this species, aluminum trichloride, a single molecule AlCl3. And again, you probably had in inorganic chemistry classes already, you know that this is not how aluminum trichloride exists in solution. It depends on the solvent. Even in the solid state, it actually has a different form than that. But the number that is reported in Goodman-Beckett or fluoride ion affinity refers to this specific species. But surprisingly enough, I mean, we did all these traditional measurements as well when we established our method. is if you do the Goodman-Beckett method with aluminum trichloride, which is basically reacting aluminum trichloride with this phosphine oxide, you get a phosphorus NMR spectrum that looks like this. There's 10 signals in there. And remember, Goodman-Beckett said, you said the shift of the Lewis acid coordinated to the phosphorus, you relate that to the non-coordinated phosphorus oxide, and that delta gives you the Lewis acid strength. But which peak do you take here? Do you take the one that's the tallest one because that's the majority of it? Or do you take the one that's the most low field shifted? There's 30 ppm difference here. So again, if you want to pinpoint the absolute Lewis acidity of aluminum trichloride, the Goodman-Beckett method fails miserably because there are different species in solution, and here's just a selection of them that can occur. You may have some monomers in there, you may have these ion-separated pairs, you may have clusters of it, dimers, trimers, and you name it. They all can interact with the phosphine oxide here, and that gives you the selection of molecules. So there's a problem when you have these, when you refer to absolute Lewis acidity, because you not always have a single species in solution. So we really want to make sure that we incorporate all these things in one measurement. And this is what our method does. So on first sight, it looks very much similar to the Goodman-Beckett method. So we use actually a phosphol oxide, and we coordinate a Lewis acid to that phosphol oxide. And the notion here is that if this is a strong Lewis acid, we will polarize this bond strongly. If it's a weak Lewis acid, we will polarize this bond weakly. We do change the energy of the sigma star orbital, of the PO sigma star orbital. Obviously, here we change it much more than we do here. And ultimately, this lowers the LUMO level of our molecule significantly more than it does it here. And this is basically here how you can see how this effect is. If you change the polarity, you get a larger, I have the video here, you get a larger contribution of this species here and a better overlap with the pi star system than you have here when it's not as polarized, the bond. So ultimately, we lower the LUMO more in this case than we lower the LUMO here. And here's just a crystal structure analysis of BCF coordinated to that to really show you that the Lewis acid indeed bonds to the oxygen here. And the important thing is that we can actually measure this or see the binding of the Lewis acid to the oxygen, which is shown here. This is a titration or an increasing amount of BCF added to our dithienophosphol. So this is, and ultimately you can see a nice shift that goes from green over yellow to orange to red. So it's a nice way to visualize this when we're adding more and more Lewis acid to this. And this is an important feature because what we are measuring is basically the relationship of the fluorescence of a non-coordinated dithienophosphol and a fully coordinated dithienophosphol. And you can actually titrate this. Oh, I took this out for time reasons. Yeah. So basically, let me just quickly summarize this here. So basically, we need an excess of Lewis acid to make sure that in the Lewis acid binding, we only have one fluorescent species in there, or the 100% coordinated species, let's put it this way, in the solution. So we usually have an excess there. Eventually, the color won't change, and that's basically the color of the adduct that we're measuring. So those are the two things we need. We need no Lewis acid coordination, and we need something that's 100% Lewis acid coordination. But to move away from that trapdoor that is the absolute Lewis acidity, we actually do these measurements with at least 3 Lewis bases. Ideally, we do it with 4, because at the end of the day, the point that we measure could easily be one of those absolute Lewis acidities, and I'll show you ultimately it is, because they do change. So we actually change the Lewis basicity of our species to some extent, because each of those species has a different pi star system that has a different interaction with the sigma star of the oxygen, phosphorus oxygen bond here. So this basically, we do modify the Lewis base strength by adding at least 3 Lewis bases into the mix. And what happens is this. So here's just the pure Lewis bases, the probes. So we have the blue one on the left, the yellow one in the middle, and the green one on the right. We coordinate weak Lewis acids. You can see that the color changes are as such that, again, the dark blue becomes light blue, the yellow becomes orange, and the green becomes sort of this greenish yellow. When we add a strong Lewis acid, the blue becomes green, the yellow becomes red, and the green becomes sort of this yellow orange here. So again, we're moving along the optical spectrum from blue to red, the stronger the Lewis acid is. And ultimately, we have a starting point, and then we have a delta to the Lewis acid adduct. All right. So originally we thought, okay, that's great. Let's measure this, and the redshift of this can easily be measured, and we can derive the Lewis acid strength from that. But if you look at this, this is all the emission spectra that we get from all the Lewis acids that we measured, and you can see even when you zoom in, they're quite bunched together. So if you just look at the emission maximum, it's quite difficult to get some useful information out of that. Here's a couple of dashed lines that I would highlight. So one of them is, again, our BCF, the perfluorophenyl borane, but also a species where the para-hydrogen in the phenyl groups is, para-fluoro in BCF is replaced by a hydrogen. So minor change, this is a para-hydrogen substituent. And if you look at the two curves, they're almost identical. But people have established in the past that no, they actually have a slight difference in Lewis acidity. They're close to each other, but they certainly have a different Lewis acid strength. So just looking at the emission maximum doesn't really help here. But we did notice that when you look at the color of the solution, so here we have the parahydro species and here's BCF, so you can see there's different shades of green that we noticed. And say, that's interesting. And then we realized, yeah, these different shades of green actually take into consideration the entire emission spectrum, not just the emission wavelength. And you can actually measure this. This is called chromaticity. This is something that's well known in the lighting industry, actually. For those of you who have never seen this, this is shown here. It's a chromaticity diagram. The colors in this parabola here, this is all the colors that we can see with our naked eye. And the lighting industry has found a way to actually make this easy to read in terms of coordinates. So you can see here we have an X and a Y axis. And basically, you can define any type of color that we can see with our naked eye by a specific X and a Y axis. And that's basically the hue of the saturation and the hue of our solution. And an interesting thing that we noticed, in particular, Josh Gaffin here was a postdoc who actually had a minor in math. He was really critical to develop this method here. He knows when we plotted the emission, so the chromaticity of the Lewis acid base adducts in the CIE diagram, we saw this parabolic function that developed, and Josh was able to fit this with almost 100% fit here. So there's clearly a mathematical correlation with the Lewis acid strength parabolic fit that we can put here in the CIE diagram with a high precision. And ultimately, now what we then developed, and I'm going to jump in here, this is where our three Lewis bases come into play, or ideally we do it with 4, but 3 actually is the minimum you need to actually for parabolic fit. So we have a blue Lewis acid probe, Lewis base probe. Here we have the green one and the yellow one. So the 3 that I showed you before. So that CIE coordinates would be here, here, and here. And again, you can see there's kind of a parabolic function built in, and that's ultimately, again, we were able to fit that with almost 99% or over 99% precision. So you can, for the probes themselves, you can actually form a nice parabolic fit. And you can do the same for the Lewis acids that you coordinate. So here's 3 Lewis acids as an example. So here's the blue probe with a weak Lewis acid, a medium strength Lewis acid, and a strong Lewis acid. Here's the green probe, a weak, medium, strong, and the yellow one, weak, medium, strong. And each one of those, so the blue dots can be fitted parabolically, the red dots can be fitted parabolically, and the purple dots can be fitted parabolically. And when you look at the probe alone and plot one of the Lewis acids on top of them, we actually have 2 parabolas that do intersect. And they intersect at a point that is not a measured point. This is a theoretical probe, and we actually correlate that with the hard and soft acid and base theory, because the strongest adduct is formed between a strong acid and a strong base, or a weak acid and a weak base. And if you have a mismatch, that bonding energy is not right there. So we think that this spot here, that the intersect, the redshifted intersect, corresponds to the perfect match of the Lewis acidity and the Lewis base. And that's why we think we can correlate that and extrapolate that. And that's the value. There's a more math in there, but I'm going to spare you the math there. We can extract that and ultimately correlate that to the Lewis acid strength. And ultimately what it does is, because we're now looking at the entire emission spectrum, we do consider all the permutations. There may be 2 or 3 Lewis acids that bind to that, but that adds to the color of the solution. And ultimately that allows us to create an effective Lewis acid measurement that we do there. And it works really, really well when you combine it. Because again, coming back to the absolute measurement, this is what I've shown you before. That was probe 1, the blue one with the parahydro and the BCF. different shades of green. If you do that with the yellow probe, turns out we get different shades of orange, but inverted. In this case, actually, it says that this is the stronger Lewis acid than this one, whereas in this case, this one is this is the stronger Lewis acid than this one. It just reflects how close they are, and that you have to be careful with these absolute measurements, because we now average it out and determine the value at the ideal matching point. We can actually eliminate those individual absolute points. And then we can do that for an entire range of boranes, as an example. They work usually the best. So we can show here, but for illustrative purposes, I just want to show you the fluorinated triphenyl boranes. You can see basically we have an increasing Lewis acidity as a function of the number of fluorine atoms, but not always, because obviously here you can see we have 2 fluorine substituents per phenyl. Here we have 3, but here we go back to 2. So it's really the position of the fluorine also makes an impact. So it's basically a matter of -I and -M effects that we're combining here that have certain effects, and you can see a very nice trend depending on the positioning of the fluoride substituents, but also the number of the fluoride substituents. We can do it then further for other group 13 elements. So these are the ones we measured. We can plot them on the same scale. But here again, an illustrative example, basically the perfluorphenyl substituted species of boron, aluminum, gallium, indium. So we're going down group 13, and you can see the Lewis acidity decreases here, which makes sense because we have more larger central atoms, more diffuse central atoms. There's d orbitals that are now being in the inner shells that shield the nucleus as well, and that reflects their reactivity. And it's well known that the Lewis acidity decreases when we go from the top end of the periodic table to the bottom end of the periodic table. Just as a side note, this is methylallumoxane. This is a species that's very important for Ziegler-Natta polyolefin polymerization. Was never detected before because the other methods fail in determining the Lewis acidity of this, and we were able to measure this species as well. It's a polymeric species, as you can see there. And we can go on and do it for cationic species. We can do it for metals, and we can do it even for lanthanides and group 3 elements. So you can see here again on the bottom right, this is kind of very similar reflected in this. Basically, the scandium, yttrium, lanthanum. Scandium is the strongest Lewis acid, and lanthanum is the weakest one. If you go down group 3, where we can even detect some, not as clearly anymore, but we can see the changes in between the lanthanides, at least every other one, because there's some problems that some of the lanthanides themselves are luminescent. But again, the only difference here is really the population of f orbitals. So very much inner shell, and yet our method can still detect that and say that basically the Lewis acidity does actually decrease when we go from left to the right, as far as I remember. So very sensitive method. And ultimately, we can put it all on the same scale, and this is something that has never been done before. Goodman-Beckett fails when you're comparing main group elements with metallic ones. Sometimes you don't get a good NMR signal, but our method allows us now to compare a gold 1 with this with boron trifluoride or with gallium nitride. This is the same scale, so we can actually correlate all of them on the same scale, and it works reasonably well across many of them. And ultimately, we've done that now for over 60, and that all makes sense quite nicely. One thing that I should mention, and just maybe a few more minutes I want to spend on the latest iteration, because all these, to be able to compare them on all the same scale, they have to be measured at this identical environment. So all these are measured in toluene as a benign solvent that doesn't interact with the Lewis acids. But certainly, as I mentioned before, if you have a donor solvent, for example, that could impact the reactivity, and we wanted to look into that as well. So what happens when we change the solvent? How does it impact our measurements? So this is something we noticed when we did the titrations of those Lewis acids with our phosphol, or the phosphol with the Lewis acid. So originally, this is what we observed before. The solvent was benign. It was toluene. So you basically have our phosphol oxide. It binds to the Lewis acid and forms the adduct. If you have a stronger donor solvent like acetonitrile, which is a very strong Lewis base, basically this equilibrium doesn't happen, because what happens is basically the Lewis acid binds to the solvent and kills the Lewis acidity. So it can't bind to our phosphol anymore. But if you get the conditions quite just right with the right base and a solvent like diethyl ether in this case, we were actually seeing 2 equilibria happening. So basically we were able to see this equilibrium and we see this equilibrium, because this one is not 0 or 100% or 0 and 100% as before. This is sort of, there's a certain portion, let's call it 50-50 for all intents and purposes. So you can see 50% of this is happening and 50% of that is happening. So the solvent does actually play a role here. And what we found is actually that the polarity and the donor strength of the solvent have a noticeable impact on these equilibria. And the problem here is, though, that the polarity and the donor strength are not features that work in the same direction. You can see that here. I'm just going to highlight diethyl ether, which is fairly non-polar in large scale of things, but it has a very strong donicity or donor number. So it's a weakly polar but strong donating. And again, acetonitrile is a strongly polar but also strongly donating solvent that we have. So you can see that solvents can have actually effects that go in the same direction or can have effects that go in the opposite direction. We made it a little bit more challenging to determine this. But again, we were able to actually piece this together. And ultimately, this is a borane series here. Again, our favorite BCF. And then the parahydro here, we basically have an oxygen between the boron and the carbon substituent. This is a weaker Lewis acid, different degree of fluorination here. And you can see that basically within different solvents, let's take BCF as an example, ethanol significantly reduces the Lewis acidity of it, whereas the others are not so much. And here, chlorobenzene actually enhances the Lewis acidity over toluene, because this is kind of a polar solvent that can actually increase or stabilize a delta plus at the boron and a delta minus at the substituent. So ultimately, we can actually enhance the Lewis acidity if you have weakly donating solvents. But if you have strong donor solvents, we could completely shut down the Lewis acidity with acetonitrile, and that's why it's not in here. We could not measure that. Or we can have diethyl ether that weakens the Lewis acidity overall. So there's two effects, goes in two directions, but we were able to actually measure that as well. So and ultimately, the bottom line here is that solvents that are both strongly donating and polar result in a lower Lewis acidity, whereas if you have a weakly donating polar solvent, they tend to enhance the Lewis acidity in solution. All right, with that, I'm at the end, and I hope I could show you that we can use Lewis acidity coordination to a PO bond that ultimately gives us a nice redshifted emission that we can then correlate with the effective Lewis acidity of the Lewis acid in solution, and we can measure basically the entire periodic table doing that. But we also can have been able to show that solvents can have a dramatic impact on the effective Lewis acidity. And ultimately, we have these opposing effects, and you really have to be careful if you want to use a specific Lewis acid as a Lewis acid catalyst, that you get the right solvent as well, because ultimately you can kill your catalysis very effectively when you have to throw in the wrong solvent in the environment. All right. At this point, I'd like to thank a few people. Obviously, I've already mentioned, where is it? Josh Gaffin was instrumental in this, particularly his degree in math as well. There's a postdoc in the group. It really enabled the developing this. Amy Latursky did the solvent studies here. And there was a few undergrads that were involved in the work as well, because there's a lot of data points that needed to be collected. Funding agencies, I would like to highlight NSERC of Canada, which funded most of the work, and the Canada Research Chairs. And with that, thank you very much for listening, and I'd be happy to answer any questions you have.
Right. Okay, questions? Anyone has questions, comments, questions?
I think I got
Stuff in the chat. Okay. How
Sure.
widely has this method been implemented since its development?
Okay. So far, not widely, because obviously you need the probes. I mean, we are basically offering people at this point to measure their Lewis acid. So we have actually had a collaboration, a successful one, with a group in Canada. So basically, they developed Lewis acid catalysts in group 13, and basically, again, they wanted to know the strength, because for the polymerization, that worked out really nice. So we have a publication out of this. But so far, people have not used it yet, because the limiting factor right now is access to the probes. We were thinking about maybe commercializing them eventually, but we haven't gotten around this. And it's only a relatively recent discovery too. So the first paper only goes back 4 years. So and with COVID in between, I think it's basically just developed yesterday.
Right.
So but we're hoping certainly that people pick up on it.
Yeah. other questions? So I saw you answered my question about the effect of the solvents on Lewis
Yeah,
acidity, and it makes perfect sense, right?
yeah.
So have you looked at, you did ether, diethyl ether. Have you looked at other oxygenated solvents that are commonly used? THF, which is basically a cyclic ethyl ether,
Yeah, THF is
ethyl
problematic in this
acetate.
context. Yeah, it's problematic in this context because BCF, our favorite strong Lewis acid,
Uh,
polymerizes THF. So you have to be
okay,
again, you have to be careful that your solvent is not a reagent for the reaction. So you can certainly expand that. So we needed to balance this. So we try to find some elements that are, well, I mean, obviously we have to find solvents that our Lewis acid are soluble in and that they don't react in. So I can't remember, maybe we were thinking about using dioxane
okay,
because it has less tendency of ring opening, but I don't think we've done a lot of this. This is already, like I said, this was the whole Lewis acid, the solvent is more than a year's worth already.
okay,
Yeah.
okay. Question in the chat, do you see this work being put in undergraduate textbooks one day?
I hope so. I mean, obviously, I mean, I don't know. It really depends. I think the Goodman-Beckett method is something that has made it into textbooks. I don't think at least it's not my intention when I start doing research that this is something that needs to go into a textbook or that needs to actually have my name attached to it, right? So this is something that was very popular in the past. It's maybe some people that sort of needed that for their ego to actually have something like this. I mean, it's great if it ends up. I mean, effective Lewis acidity is not something, maybe I should mention that. It's not something we have invented. I mean, this is something that's been floating around in the literature a bit. We just found a way to actually effectively measure the effective Lewis acidity. Oh, there's too many effectives in there. But so it's something I would think from a practicality standpoint, I could see that ultimately people will maybe recognize that because again, aluminum trichloride is an extremely popular reagent for Diels-Alder reactions, for Friedel-Crafts reactions, right? And so there's a case to be made that you should use the effective Lewis acidity of that, and it's actually well known as well. People weren't able to actually put a theory to it, but it's well known that if you add, what was it, nitromethane to a
Right.
reaction for Craft reaction, it actually tames the reactivity. Well, of course, because nitromethane is a Lewis base, and that
Mhm.
probably coordinates to aluminum trichloride, right? So these things have been floating around in the literature. So it's not necessarily something that we have invented all of these. We've just basically put a theory around it now. For the
Yeah.
first time, we can measure these things and in a meaningful way, I guess. It may end up in a textbook. I'll be happy if it does, but I can also die happy if it never happens.
So let's say we have a metal and we change the halide. Let's pick any metal, magnesium, magnesium fluoride, chloride,
Mhm.
bromide, iodide. Can you just sort of maybe speculate the acidity, Lewis acidity as that trend, in that trend?
I would, yeah, well, it's a complex situation. It's certainly,
Right.
this is something we still want to do, and not necessarily even the coordinating anions, because I think that's very obvious, right? At the end of the day, what it comes down to, even with the fluorides, it's basically this, right? Instead of the solvent, you basically have Lewis acid cation and anion. So it's a matter of
Okay.
how much is this equilibrium favored over the other one. So I would think,
Okay.
yeah, like I said, I might take your example. I would assume that magnesium chloride probably is a strong relationship. It will probably quench the Lewis acidity, whereas if you take magnesium iodide, you would probably be more here and actually have more of a magnesium
Okay.
MgI plus as a Lewis acid in solution. So what we really want to do is test the limits with weakly coordinating anions to see if
Right.
there's a little bit of a contact. So basically, again, ultimately we may be able to actually see this year where you replace the solvent with anion
Right.
and see how
Okay.
much this equilibrium is there. We haven't gotten around that, so we're certainly, so my colleague Chris Caputo and I we're looking for a joint grad student to actually tackle that, but we haven't been
Okay.
able to hire one yet.
All right. Okay, well, are there other questions, comments before we take off? I learned a lot. I'm very interested. I'll be calling you
Thanks.
up offline here
Okay, sounds good.
to ask you some other questions related to this work. But thank you so very much for this presentation today.
Well, thank you for having me. It was fun.
All right.
All right.
Okay,
Okay.
take care. All right.
Have a good one. Bye-bye.
Bye-bye.